I intend to consider the simplest case, ordinary differential difference operator and problem of eigenfunctions and eigenvalues for this operator. But it will be the following difficult place. I consider neutral delay differential equations. Neutral. This means that we have shifts in the derivatives of higher order. For the first time, generalized solutions of boundary value problems for differential difference equations on a finite intervals were considered in papers of G.A. Kamensky and A.D. Mishkis, and later by A.G. Kamensky. And what was interesting, that it was shown that smoothness of solutions can be violated at interior points of intervals, even for infinitely differentiable right-hand sides of the equation. This was a little bit astonishing effect. Moreover, this phenomenon can have bad influence on the opportunity of applications for numerical methods. Nevertheless, it was proved, and therefore later number of papers were devoted to investigation of smoothness of generalized solutions of differential difference equations having neutral type. First of all, let me mention that such equations have important applications in control theory. I mean papers of Krasovsky, Osipov, and many other famous mathematicians. Later, conditions on the right-hand sides of differential difference equations, which provide smoothness solutions, were studied in papers of myself and my pupils, and it was, in fact, important opportunity to achieve some smoothness. There also arises the following question: under what conditions on coefficients of differential difference operator smoothness of generalized solutions of boundary value problems for such equations is preserved on the whole interval for any right-hand side? Not conditions for the right-hand side which provide smoothness, but conditions for coefficients which provide smoothness for any right-hand sides. And what was interesting, that if we have even at least one term with derivatives having shift of argument, then smoothness for some right-hand sides can be violated. We consider in this lecture another problem which is connected with smoothness of generalized solutions. It's much more complicated because in previous problems we could choose such some function belonging to domain of operator, which is not smooth enough, roughly speaking. But in this case, if we apply differential difference operator, we cannot obtain arbitrary function from L2. We must obtain function multiplied some number lambda, which is eigenvalue. So we shall consider the following problem. We'll generalized eigenfunctions of differential difference operators preserve their smoothness on the whole interval or not. Let us consider, let us consider difference operator R acting from L2 into L2 on the whole real axis by the formula 1. Alpha sub j are some complex coefficients. And here we have shifts of argument. Generally speaking, we can have both delay and retarding. Let Q be an interval 0D, where D is equal to N is some natural number, and plus theta, and theta is greater than 0 and less or equal to 1. So generally speaking, N is not integer part of D. This is very convenient for the consideration. So please pay attention that N plus theta and theta is greater than 0, less or equal to 1. Now, the shifts of arguments in the operator R can map points of the interval Q outside of Q, R minus Q. Therefore, if we consider later differential difference operators, we must put boundary conditions not only at the ends of interval, but also in some neighborhood of these ends. For this purpose, we introduce operator R sub Q acting from L2 of Q into L2 of Q by the following formula. What is I sub Q? I sub Q, this is operator of extension by 0 of a function from L2 of Q to L2 R minus Q by 0. PQ, this is operator of restriction of function from L2 of R to Q. So what we are doing here? First, we consider extension of function by 0 outside of Q. Then this some function is determined on the whole real axis, and we apply difference operator, weighted shifts, sum of weighted shifts. Then again, we restrict our consideration on the interval Q. Later, we shall use some partition of the interval Q into some subintervals, which is formed by deleting the orbits of its endpoints under the group of integer shifts. Then, if theta is equal to 1, we obtain only one class of disjoint subintervals, Q1k, having the form k minus 1, k, for k equals to 1, 2, and so on, n plus 1. If theta is greater than 0 and less than 1, then we have two classes of disjoint interval. Q1k intervals of the form k minus 1 plus theta, if k equals to 1, 2, and so on, n plus 1, and q 2k, which is equal to k minus 1 plus theta, k. K equals to 1, 2, and so on, n. And we define the vector function u capital S, u small of x, given with the following coordinates, u s1, u sn, by the formula 2. What does it mean? Instead of, for example, if we have integer length of interval, so the case when theta is equal to 1, instead of function u, which is defined q, which is defined on the interval 0 and n plus 1, we consider vector function u sub s u small with coordinates which are obtained with the help of shifts of arguments. But all coordinate functions, all coordinates, are given on the same subinterval q s1. In our case, if theta is equal to 1, this will be q 1, 1. If theta is greater than 0 and less than 1, we have two classes of intervals and, of course, two vector valued functions. u1, u small, u capital 2, u small. We denote by R1 n plus 1 matrix, or matrix of order n plus 1 and n plus 1, that has the following form. This is Toeplitz matrix, and it consists of coefficients of difference operator of the following form. So we have along the main diagonal alpha 0, then auxiliary diagonal alpha 1, and so on, and below main diagonal we have alpha minus 1, and so on. So this is Toeplitz matrix. Matrix R2 of order n have the following form, and it can be obtained from R1 by deleting the last row and the last column. Lemma 1, the operator RQS given by the following formula and acting from L to n of QS1 into itself is the operator of multiplication by the square matrix RS. What does it mean? You can see easily that this operator is unitary equivalent to operator RQ if we consider this operator on the subspace of L2 consisting of functions which are defined on the union of such subintervals, and outside this union they are equal to 0 identity. In other words, instead of operator RQ, we can consider the matrix R1 if we have interval of integer length, or two matrices R1, R2 if we have non-integer. Instead of difference operator, we can consider either one matrix R1 or two matrices R1 and R2. They determine all important properties of the operator RQ. Now, we introduce a differential difference operator AR with domain D of AR. This is unbounded operator in the space L2. It's given by the following formula. A sub RU is equal to minus D to dx twice RQU. And the domain of this operator consists of functions U from the Sobolev space W210 such that RQU belongs to W22 of Q. Definition 1. A function U, which is non-trivial, the domain of AR is called a generalized eigenfunction of the operator AR corresponding to an eigenvalue lambda if ARU is equal to lambda U. This is more or less a natural definition of eigenvalue and eigenfunction. But we have some questions which are connected with definition of this operator A sub R. Let me explain. First of all, why should we consider multiplication of operators in the following order? Differential operators multiplied on the right to differential. Why should we not consider inverse order? RQ multiplied differential. The reason can be explained as following. Majority of problems arising in natural sciences, in physics, in control theory, and so on, in engineering problems, and so on, can be derived from variational problems. And in variational problems, if we have function containing first order derivatives with shifts, then we must apply to them, if we consider corresponding Euler equation, we must apply to difference operators multiply some first order differential operator, from the left another difference operator. First order differential operator and operator RQ are commutative, but second order differential operator and difference operator are not commutative. Therefore, we shall never obtain natural differential difference operator of neutral type from variational problems. And usually they have no physical sense. Second, of course, such problems will be trivial because if the difference operator is invertible, you can see, and if it is standing here at the left part before differential operator, we can multiply both sides here by difference operator and remove it to the right part. But in this case, we cannot do it. It must be inside. Difference operator must be inside. And the third reason, that if we consider function u from this space W210, then so u must satisfy homogeneous Dirichlet conditions. Then function RQU will also belong to Sobolev space W21, but with non-local boundary conditions. Therefore, boundary value problems for differential difference equations are closely related with so-called non-local boundary value problems, in particular with well-known Bitsadze-Samarsky problems. But for the simplicity, I consider only one-dimensional case. In this place, I explained you why such formulation or definition of operator looks necessary. Now, example 1. Let us define difference operator R by the following formula. This is the simplest situation. We have shift to the left by 1. We have shift to the right by 1. Interval 0, 3. In this case, theta is equal to 1. We must put homogeneous boundary conditions on the interval -1, 0. Of course, for without loss of generality, we can set them on the whole semi-axis, but it's enough to put them on the interval -1, 0 because we have only shift of x -1. And on the interval 3, 4 here, on this interval. And let function has the following shape here. Then we must extend this function by 0 outside of our interval. Then we must consider all all parts of this sum together with some all shifted terms, term without shift, and then we must restrict ourselves to interval 0, 3. And finally, we obtain RQU. This has the following. And what's interesting here? Function RQU can be obtained from function U, which belongs from W to 1, 0. So it has regular first derivative. But, and this function you see is smooth enough. But function U, as you can see from this picture, can have discontinuities at the points 1 and 2. The left and the right derivatives at the point 1 are not equal. So at the point 2, we have the same effect. But when we consider this sum, this operator, RQU, already we obtain sufficiently function. I especially explained very carefully this very simple example, because later we shall use this example for explanation of some new effects for eigenfunctions of differential difference operators. Now, definition 2. We say that the differential difference operator having this form satisfies the strong ellipticity condition if the matrix R1 plus R1 star is positive. This is Hermitian adjoint matrix. If positive, definite. You see here, we use terminology from PDE, from elliptic theory, though we consider ordinary differential difference operators. And it's naturally because functional differential operators, generally speaking, are locating between ordinary differential equations and partial differential equations. More than this, usually if we consider boundary value problems, they are more closely related with partial differential equations. Theorem 1. Let the operator A sub r be strongly elliptic. Then the spectrum sigma of A sub r is discrete, and it belongs to right part of complex A. If moade alpha sub j is equal to alpha complex adjoint minus j for all j, then the operator A sub r is self-adjoint and spectrum belongs to positive semi-A's. So this is more or less natural result. Nothing astonishing. Theorem 2, concerning smoothness of generalized solutions. In this case, it's not necessary to demand a strong ellipticity. We assume something not so, we consider not so strong assumptions. Namely, let determinant of R sub S is not equal to 0. So S is equal to 1, 2 if we consider non-integer interval, and S is equal to 1 if we consider integer interval. And let U, non-trivial function, be a generalized eigenfunction of the operator A sub r, corresponding to the eigenvalue lambda. Then we can guarantee smoothness of eigenfunction only on such subintervals, in the case theta equal to 1, and on the whole system of two different smoothness on two systems of subintervals, j minus 1 plus theta, and j minus 1 plus theta. And What about interior points, orbits, or the ends of intervals? This is a problem which we consider later. Remark 1. If the operator A sub r is strongly elliptic, then determinants r sub s are not equal to 0. So for strongly elliptic operator A sub r, assumptions of our theorem 2 hold. However, we have the following question. Is the smoothness of generalized eigenfunctions reserved on the whole interval 0d? To answer this question, as you can guess in advance, I hope you have already guessed, we must reduce our eigenvalue eigenfunction problem 4 to a system of ordinary differential equations with spectral parameter lambda and with non-local boundary conditions. So we restrict for simplicity ourselves to the case theta equals 1. If u is a generalized eigenfunction of A sub r corresponding to eigenvalue lambda, then equality 4 can be written in the form of system of ordinary differential equations 5. This was the main purpose of the determination of our matrices R1, R2. In this case of integer interval, we don't need R2, only R1. So we should write here R1 V prime prime is equal to lambda V. But if we apply inverse matrix to the left and to the right parts, we obtain the following system of ordinary differential equations. But the most interesting thing here are to determine in correct way boundary conditions. Let us come back to our example. Sorry. You see, here we have 0 on the left end. We have a little bit different situation, interval 0, 2, but in any case. And here also we must have 0 on the right, on the right end of interval. So jointly, we obtain V1, this is the first coordinate. It must be equal at 0, it must be equal 0, Dirichlet condition. But the last coordinate function, n plus 1, must be equal to 0 at the point 1. Because we shifted all parts of our eigenfunction V. Now, what we have in addition? In addition, we have continuity of our function at interior points. Because the domain of our operator consists of functions from W2, 1, 0. What does it mean? This means that this space belongs to space of absolutely continuous functions. If function belongs to this space, then it is absolutely continuous. Therefore, the left and the right derivatives at interior points must coincide. Now, we have this very condition, 8. Now, it remains to put plus n boundary conditions. But how can we determine them? Again, let us consider definition of eigenfunction. RQU must belong to W22. You see? Because here we have lambda U. This is regular function. If we should have discontinuities of this function here, we should obtain in the right-hand side delta functions. but it's not the case. So RQU must be sufficiently smooth. It must belong to W22. What does it mean? This means that derivatives of RQU at interior points, in this case, this is 1 and 2, must be smooth. The left derivative here and the right derivative here must coincide. The left derivative and the right derivative at point 2 also must coincide. But since we are using matrices R1 and R2 and vector functions, sorry, is there a question? No.
No
Okay.
question, no.
Then I'll continue. So this continuity or the third derivative of the function RQU can be formulated with the help of equalities 9. Lemma 2. General solution of the system of ordinary differential equations 5 has the following form. 10. We can represent them in the form of matrix-valued functions, where n plus 1 vectors C0 and CO from the word odd and CE from the word even are arbitrary coefficients. Substituting 10 into boundary conditions 6, 9, we obtain system of linear equations. A of lambda C is equal to 0. Of course, in every particular case, this matrix, depending on parameter, can have some particular form. And necessary and sufficient condition for system 11 to have a non-trivial solution is that determinant of A of lambda is equal to 0. Thus, the set of eigenvalues of the operator AR coincides with the set of roots of the determinant of A from lambda. Now, if we additionally require smoothness of generalized solutions, generalized eigenfunctions, over the whole interval, in other words, U, if we want to have U from the space W to 2 on the whole interval, then we must add two conditions, 6, 9, the following additional conditions. This means that not only function RQU, but also function U itself must have coincidence of first derivatives at interior points. Sorry. So we mustn't have such situation. Here we must have coincidence of left and right derivatives at orbits or the ends of interval. Here we also must have smooth functions. These conditions have the form 12. Then in the general solution of system 5, in the form 10, must be substituted into 3n plus 2. We add n plus to n plus 2 conditions, more n conditions. The boundary conditions 6, 9, 12. We add conditions. And the question is connected with the following. We have obtained system 13, where this system will have non-trivial solution for lambda corresponding to eigenvalues or not. Theorem 3. Let the operator A sub r be strongly elliptic. We assume also for simplicity for theta equal to 1, and determinant of A of lambda is equal to 0, this means that lambda is eigenvalue, then there exists a generalized eigenfunction U, which is not smooth inside, which belongs to W210 minus W22, corresponding to the eigenvalue lambda if and only if the rank of matrix B of lambda is greater than the rank A of lambda. This is more or less clear. But what's the most interesting? This is example 2. Let us define difference operator R by the formula 14. Here, alpha is some irrational number, which is the modulo of lambda, and the modulo of lambda is less than 1. In this case, we have the following matrix R1, 1 alpha, alpha 1, and it's easy to see that in this case, the matrix R1 is positive definite. This means that we have strongly elliptic operator with real spectrum belonging to real semi-axis. And let us consider now eigenvalue, eigenfunction problem 15 for the operator AR. Let Vk be given by the following formula. So we are reducing our boundary value problem for differential difference operator to a system of ordinary differential equations with some conditions, which we described before. Then generalized eigenfunctions have the following form, 16, 17. But now, in order to determine these indefinite coefficients, we must insert them into boundary conditions. For example, the first boundary conditions must be given as following. V1 of 0, let me show you. V1 of 0 is equal to 0, 6. In all situations, we have the same boundary condition. You see, V1 of 0, this is exactly sum of C1, C2, C3, C4. In the same manner, we can obtain other 3 equations for determine eigenvalues and eigenfunctions. Now we must calculate determinant and consider equation when determinant is equal to 0. This determinant consists of 3. This is a product of 3 functions. The first one is the following, the second is the following, and the third is the following. So we have 3 opportunities. First branch of eigen values is this, and corresponding eigenfunctions you can see here are signs. Eigenfunctions are smooth. We have a countable set of smooth eigenfunctions, but also we can have the following opportunity, 23. In this case, we have the following eigenvalues, and corresponding eigenfunctions have the following. Again, we have smooth eigenfunctions, but transcendental equation 24 is much more complicated. Again, it has infinitely countably many roots, but let us continue. Let us add additional condition which provides preservation of smoothness of eigenfunctions at the point x equal to 1. This is condition 12. In the case of interval 0, 2, we have only one interior point, 1, and we have such condition at the point 1. We have coincidence of left and the right derivatives at this. And corresponding condition for constant C1, C2, and so on is the form 25. Now we can verify that conditions of theorem 3 are satisfied. What was shown that equations 18, 20, and 25, we must study them and show that if lambda is a root of 24, equation 24, then lambda 1 is not equal to 0. And the rank of system 12, 21, 25 is equal to 4. The determinant of system 18, 20, and 25, instead of 24, we add here 25, is 0 in the following case. Here we have equation 28, which looks like different from 24. And it was proved that for irrational number alpha, which is not equal to 0, of course, equations 24 and 26, 24 and 27, 24 and 28 have no common roots. Therefore, if equation 24 is satisfied, then determinant delta 1 is not equal to 0. And the rank of system 18, 21, 20, 25 is equal to 4. Then we have different ranks of matrices A of lambda, which is equal to 3, and B of lambda, which is equal to 4. From theorem 3 in this case follows, then eigenvalues lambda of the operator R correspond to the generalized eigenfunctions U from W to 1, 0 minus W to 2. So we obtain, in this example, countable set of eigenvalues with eigenfunctions which are not smooth. We have 3 branches of eigenvalues. For 2 branches of eigenvalues, we have smooth eigenfunctions, and for the 3rd branch of eigenvalues, we have non-smooth eigenfunctions. Now let me mention that results which I presented here were published in our paper, which was published in our paper in journal Mathemатические заметки, Mathematical Notes, last year. This work was supported by Mega Grant for Russia, which we have won 2 years ago. And now about bibliography. As I mentioned at the beginning, for the first time, a neutral differential difference equations with boundary conditions were studied in papers 1, 2. The following papers 3, 4, 5 were devoted to problems for control systems with delay. In particular, Krasovsky problem, so-called problem of damping control system with delay. Now in papers 6, 9, it were studied sufficient conditions for right-hand sides of the equations which provide smoothness of solutions. They can be formulated in a very simple way. Right-hand sides, of course, in different cases where different options must be orthogonal to finite number of functions in the space L2. This provides smoothness of generalized solutions. And also paper number 10. And in papers 11, 12, we considered another situation, as I told you at the beginning, which conditions for coefficients provide smoothness of generalized solutions for any right-hand sides. And it was proved that this phenomenon will take place only if all coefficients, if we have constant coefficients in the terms with shifts are equal to 0. In the case of variable coefficients, we must have 0 coefficients at the orbits of the ends of it. That's all. Thank you very much for your attention.